Okay, gotta end this one with a few warnings. Really, what you need to do is practice those techniques, watch other people do them, explain them to other people, but we have to make sure that you don't go wrong along the way. So here's a few places where people will often make mistakes, as well as techniques to deal with them. Okay, warning number one, x cubed minus x as x goes to infinity. Well, it looks like we have infinity cubed. That's going to look like an infinity. It's going to get bigger and bigger and bigger as we go to the right. This is also an infinity. We have infinity minus infinity. What could go wrong? I know what you're saying. Infinity minus infinity, that sure sounds like 0. Sorry, kids. You do not get to subtract infinities. I don't know what that is. Really, that's saying a really big number minus a really big number. Or rather, increasingly big numbers subtracted. And I don't know which is growing faster. And so this is actually more of like a competition between x cubed and x to see which is going to grow faster. So we never, ever, ever get to subtract infinities, just like we don't get to divide infinities just because they're infinity. All right, so what do we do? It's the same thing we do a lot when we have cases like this. We factor. Factoring is our friends. So I can pull out an x. Great. Oh, I should probably keep that limit there. Never forget that limit if you're not done with it. Okay, so not equals. What's happening here now? It looks like I have something going to infinity times something going to infinity. Okay, so bigger and bigger numbers times bigger and bigger numbers. I am much more confident that, my friends, is going to be infinity. Great. Another way of saying this is, yeah, x cubed 1. It's totally going to dwarf out this minus x. All right, so factoring often your friend. Okay, over here on number 2, if we tried to plug in, it looks like we get something going to infinity minus something going to infinity. Very familiar, very similar. I don't really know how to factor this. I don't quite know how to deal with that square root. But this does look familiar. So if you're in a case like this where you want to factor it, but you've got this square root in the way, we have one trick for dealing with those kinds of roots. And it's a little different from our one from before because this is not a fraction. So instead, what I'm going to do, maybe you know it, we're going to rationalize that thing by multiplying by the conjugate. And that'll actually give us a fraction. Okay, I'm going to leave it there for you. Go ahead and multiply that out. And then from there, you might still need to do a little bit of work. But I believe in you. You can do it. Just reminding you of that old friend multiplying by the conjugate. Okay, one more, because we haven't seen any where the limit just doesn't exist yet at all. X times cosine of x. What does this look like? Well, here is my attempt at drawing x. Here is, say, negative x. Oops. Why did I just sketch those? Well, cosine just goes up and down between 1 and negative 1. X is going to bound its amplitude. So it's going to stay between x and negative x as cosine goes up and down. So this is going to look, see if I can draw this, just steeper and steeper and steeper. Okay. So it should have a constant period. I'm not doing a really good job of drawing that, but there should be the same distance between each of these amplitudes horizontally. Okay. So the question is, what happens as I go way off to the right? Right? What happens as I go all the way out this way? And it is getting bigger, but it's also getting smaller, and then bigger and smaller. It hits 0 as many times as I want, and infinity as many, well, not infinity, it gets as big as you want, but then it goes back to 0. And then it goes to the negative side. And the question is, what do I say in this case? It doesn't really seem fair to say it's going to infinity when it's also going to negative infinity and it's also going to 0. And limits for us are only going to exist if they're consistent, right? You've got to keep getting bigger or keep getting smaller in the long run. And so because this goes back to 0 as many times as you want off in the distance, we are just going to say this friend does not exist. Okay, So it is still possible to have does not exist, and usually what that means is you have some kind of an oscillating motion like this, where it doesn't settle down to bigger and bigger or smaller and smaller or any particular constant. Okay, that is it. Practice lots. Kind of a shorter lesson on this one because really you should just work through a lot of examples, I think, in this case. One final thought that is worth sharing, why this is important. End behavior is really important for all kinds of things because that's telling you how will things settle down. So if I want to know what is the maximum population for a species, it's probably looking at the end behavior of a population model. If I want to say, hey, what's going to happen in the long run for a chemical reaction, which may just take a couple of seconds, well, that is the end behavior. That's the asymptotics. So that is as x goes to infinity. Many things that even don't take that long, what you care about is what is that limit as x gets very big. That's where things are going to stabilize. And oftentimes these are called equilibrium points. And so that matters a lot in many fields, not just because mathematicians want to talk about infinity. So I'm sure I'll talk about that more because I like talking about it. But until next time, my friends.